Okay, this is Ag Econ 552. This is our first lab session. Just to make clear, this covers some material that's found in the document that we have been using as a reading or sort of a guide. It's called Notes 1.2, or I think it's the heading on it says Instructor Notes. And then also this is in Kaiser and Messer Chapter 1. I will tell you right now, this recording setup comes in a little low, so be sure that both your speaker volume and the volume on your computer you're watching this on are turned up. This is as loud as I can get the source recording coming to you. Okay, just some reminders. This online lab period does replace in-class meeting, and so this is one of those times when we're swapping online class for in-class. We'll have other videos where that's not the case. I'll always let you know. The way that you deliver or show that you've completed this lab is to take the online quiz that'll be posted, and so that'll just be some simple calculations or showing that you got the results from the lab. It's mostly about completion or participation or showing that you've been through it. The due date will be set for noon the day of our next class meeting. So whenever I assign one of these labs, it's supposed to replace our class time, and the idea is that you could take that 75 minutes and be through with the presentation of material. So whatever quiz or sort of online documentation you're supposed to prepare needs to be ready by the next time we meet, because I'm going to usually just pick up right from the lab, the end of the lab session. In terms of materials, everything is posted on Blackboard in the Lab 1 location. So you'll see these slides, which are the part of the notes that you might need. The other notes are that document titled Instructor Notes 1.2. So several pages out of that cover this example and cover the instructions for Solver. I believe it's probably possible you could get through the entire lab sort of protocol, the basics of solving this model, just by reading through those set of notes. I am going to ask that you at least go through this lab video as much as possible, because I will be adding some things that aren't in those notes, but they would be somewhere else. So, use your conscience as your guide. We'll also be covering some stuff from the book chapter, chapter 1. So I think we're on the first 20 pages of the textbook. So we'll be talking about that. This video presentation is also linked there, and then of course the spreadsheet that I'll be using. I think it's called Brewer's Problem, and that's also linked there. So take that spreadsheet and you'll have what you need. Okay, our problem setup looks like this. So again, it is one of the examples. It's example 2 in chapter 1 of the book. And it is, I've talked about a little bit in class already, this cheap versus premium brew. So it's a brewer who has two products. The products both take up resources, and in terms of resources, we're talking about sort of assembly line or production lines. And so we are not in this problem saying that production line 1 precedes production line 2 precedes production line 3. That's a pure bottleneck type problem, but it also has a network flow condition that we are not ready to do yet. So we're going to assume that each of these lines starts the decision period or the planning period ready to process product. Okay, and so if that bothers you or that feels like a cheat, that's fine. You're correct to assume that in addition to sort of the resource limit constraints, the amount of material coming off of line A ready to go in line B could be an important piece of this problem, and it's certainly one we'll deal with later in this semester. But for now, we're just going to say they use up hours that are available, and these are the rates at which a single unit of the brew cheap brew uses up this line, the pre-fermentation operations, 3 hours for every unit of cheap brew, 3 hours for every unit of premium brew. And then the total amount in this planning period that we're solving the model for is 50 hours. You can read through all the constraints that way. And then down here at the bottom, we have our last sort of piece of information, the profit per unit. So $1 per unit of cheap brew, $2.50 for premium brew. The coefficients here, these sort of fixed usage rates, or what we call parameters. These are all actually parameters given the definitions we went through in class, but these are sort of the pure parameters of the problem. And then we have these fixed resource limits that are what we would call exogenous variables. They're things that we would think under some conditions where they are allowed to hire and fire people, these things would be under the control of the planner. And then to some degree, you could imagine a decision maker being able to move or change these profit levels by changing the price that they charge. Okay, but we're going to say they're fixed. They're on some kind of market pricing right now, and that means all the sort of payment levels and prices are fixed. We should talk about the definition here being profit per unit. We're using profit in its most general sense to mean whatever the objective is. And so it could be the profit measured as the return above variable cost, because we definitely know that the way we're getting the cost in for this operation and bottling and quality control is through these resource limits. We're not actually, any charges we make would be for the full amount over here, not for the per unit usage of these, because we don't know yet how many of these upper bound limits that we're going to use. And the assumption, once we write over here that these limits are in the problem as sort of these fixed variables or exogenous variables, is that they're already paid for. So that money is sunk cost. And so now it's just what's the efficient way of using those. The modeling process we've talked about mostly in an algebraic sense in class so far, but it's certainly the case that when you start to build a quantitative model in a computer setting, that you would go through roughly the same procedures, the same process. That would include making sort of declarations, right? So we are going to declare what symbols represent different things. So that would be the symbolic declarations for variables and parameters. So we started this a little bit when we said let's label things and decide which are parameters of our problem and which are variables, and then we need those symbols just as a shorthand. And so we're going to use R for the profit or the objective variable, and we'll use C for the activity level or the production level that goes with the cheap brew, and then P for the premium brew. After we've done declarations, we could have some more of these, but we're going to have values. We already have our table here of values for the coefficients, for the profit equation coefficients, and for the right hand side, so we don't really need to declare symbols for those. We have numbers for them. So the unknowns are the things we need declarations for, and that's what we have here. Second, we need to define the objective equation. So once you've declared the variables, you start declaring or defining the equations of your system. So we would define this objective equation that would include which direction our optimization goes in. In this case, we're going to maximize the returns. The next step would be to define the constraints, and those are just the set of equations and inequalities that provide limits. So we don't produce these things without bound. We have limits on how much we can make, and those will be defined by the resource constraints. We always precede this by subject to, so there has to be some signaling either in the algebraic problem. We always know the signal for this is once we start reading under this subject to, that means it's subject to the following constraints, subject to the following limits. So we'll need some kind of marker that says we are now looking at constraints or the feasibility conditions when we're looking in the computer problem. And then we have non-negativity constraints. And so these are often implicit. Lots of times we won't even write them down, but for now we'll make it a point to note these out. But you can understand why people might just assume that these are going to hold, or assume that people understand, because it makes no sense to have a negative value for the level of production for cheap brew, right? Or for premium brew, right? So these non-negativity constraints, they work on the activities or the choice variables, and in this case there's no choice that makes sense that we could even sort of logically talk about when those are negative values. Okay, the algebraic look at this problem again is from your notes, and it has all the pieces we talked about in sort of setting up our model building. So we have the maximization here, the objective variable, this outcome variable of returns above variable cost, or we're just going to shorthand call that profits, the choice variable C, the choice variable P, and so their coefficients from the profit per unit multiply C and P in this equation. So you get $1 of this profit measure from every unit of C, $2.50 from every unit of P, and so this equation just says multiply C times its return, P times its return, add those together, and you give me the total measure of return. Okay, and then we have a label out here just making sure that we understand this is our objective, and then down here we have all the different constraints of the problem. So subject to, that's our signal. Everything down here is going to limit the feasible choices, and so we just have 3C plus 3P, and then we have this important signal here, important designation. Is this an upper bound or a lower bound? Well, these are all upper bounds for these three constraints, so you can use up these hours or this time available on the pre-fermentation part of the production line up to a unit of 50. Okay, so every time I use or decide to produce a unit of C of the cheap brew, that's going to claim 3 hours of my available 50 hours. And then the same thing happens every time I produce a unit of the premium brew. It's going to claim 3 hours on this pre-fermentation constraint. So we have 50 here, so all the combinations that use up 50 are available to us when we consider only this constraint. If we move down to the bottling constraint, every unit of cheap brew will use 2 of the available 40 hours. Every unit of the premium brew will use 4 of the available 40 hours. And again, this this boundary 2C plus 4P equals 40 would tell you all combinations that use exactly all 40 units. But it's also a less than or equal to constraint, so you can do the ones that use 40 or the ones that use less. If we look at this constraint compared to this constraint, we notice immediately, or we should start noticing immediately, these kind of differences. If these are the usage rates on this side, and these are the limits on this side, well, we can get some good information. They both face the same total limit. Here, doesn't matter what you think about, how you think about this problem, 50 is the grand total, and 40 is the grand total here. But every unit of C and P will use that amount, will use up this pre-fermentation time at the same rate, because they have the same coefficient of 3. But in the second constraint, we see that bottling time is only used up half as much by the cheap brew as by the premium brew. Okay, so in some sense, even though we're not talking about cost in an explicit term, this is a limit to the firm, this 40 hours, and so using less of that makes this a cheaper cost or a lower cost item when compared to the alternative, right? So cheap brew is relatively cheap, obviously, in production when we're looking at the bottling constraint. And then if we move to the last constraint, already thinking about that, it's even more of a disparity. So in this case, the item C is only using bottling time at half as fast as the premium product, but it's only using quality control time 1/3 as fast. Okay, and so it's even less, or it's even more valuable in terms of getting a lot of product out, given our limits on quality control. Okay, so our step though, or the key, or the objective of this lab, is to go from the algebraic setup of the problem, looking at the numbers, and find a way to put that into a computer solution method, right? So put it into a computer program and have that handle the solution for us. Okay, so we've seen already that this is a 2-variable problem. We could do the graphing, and when we open the spreadsheet here, you'll see that I've actually done some of the graphing work in the spreadsheet. But we want something where we put all the information together, let the data, let the computer know what the relationship is between the choices up here, the profit equation coefficients, the constraint coefficients, and the right-hand side are these upper bounds. Let the computer know what those all are, and then let it work and find the solution for us. Okay, so now you should open your spreadsheet that goes with this lab, and you'll see that there are a few different sheets here available. The one we're going to work in this lab period is only the brewer problem, so the first sheet that opens. You would also find one that says feasible space, right? And so that's a graph that lets us see all the constraints. Here's one that focuses on calculating the corner points. That's something we'll go through in class later. And then you'll see here that there's a graphic where I actually plot what would be the profit function. Well, and that's in the handout that we're working through right now, that notes 1.2. So if you're reading, you'll be able to see what's going on there. But for now, we're just going to focus on how to get this problem into a spreadsheet. Okay, so if our setup is about declaring variables, declaring equations, declaring the objective, declaring the constraint equations, and then making sure that we have non-negativity, then those are the things we should check on, and those should also guide our work in the spreadsheet. And so everything that we're going to work on is up in this piece of the spreadsheet. So there's some other work down here that we'll talk about in class when we come back and work on after we've figured out how to solve these things in Excel. So restrict your focus up here. That's where we're going to be working in this lab period. But I want to keep that stuff down there in case I need to refer to it. Okay, so the basic setup here up in this top part that I've highlighted though is you see I have a column here labeled C is equal to cheap, and then P is equal to premium. And so the way this works is we're going to let the variables claim or identify with a column of the spreadsheet. So everything under here is going to relate to this variable cheap, and then everything under this column is going to relate to the variable premium. And then every row is going to tell us something about how that variable interacts with an equation, or in the first row here, it's just going to these cells are just going to hold on to the level of the variable. Okay, so right now I have the C equals 0 and P equals 0 entered into these cells. If you change one and put 3 in for C, and I already have all the equations built in here, that's like saying, now let's try a new setup where C is equal to 3 and P is equal to 0. Put in a value over here of 5, and you'll see that C is equal to 3, P is equal to 5. Okay, and we might as well go ahead and look down here, and you'll see what's going on is when I try a solution or try a setting on the variables where C3, P5, we get a new calculation on the profit level. We get some calculations in this column called left hand side. So we got 24, 26, and 18, and those could all be compared to the right hand side, RHS, right hand side. These were our upper bounds or our limits on this. And so that's, this is when we come back to this problem, when we come back and Excel's given us a solution, we will read off our solution values for the cheap and premium, or C and P, directly from these two cells. Okay, if the columns here are for the variables, then the rows are for one, holding the value of the variables, and then for the equations. And so the first equation we have is the profit equation. So this row is labeled for the profit for the profit equation, and what it has are the coefficients that go with the variable. Okay, so this profit equation has a coefficient for the cheap beer or the cheap brew of 1, and for the premium brew of 2.5. If you keep moving down into the constraints, you'll see that here we have the pre-fermentation constraint. The coefficient that goes with the cheap or the C variable is 3. The coefficient that goes with P, or the premium brew, is 3. And so every one of these cells underneath a column in the equation part is going to be the coefficient that goes with whatever particular variable we're talking about. So the coefficients for cheap are 1, 3, 2, and 1. The coefficients for premium, 2.5, 3, 4, and 3. Okay, and so now normally, you would think about if you've ever done any coding or computer modeling, you want to have that multiplication written right there. So it's 1 times C or 2.5 times P, but Excel doesn't know how to do equations, right? Excel has no sort of mechanism where we could write down an equation that says take this variable, multiply it by this coefficient, and then evaluate everything, and then do the algebra, do the mathematics that I want. When we move into GAMS, the other software we're going to use in this class, that's exactly what we'll be doing. We'll be writing down the exact sort of algebraic type problem, and GAMS knows how to work with that, but Excel doesn't, so we have to work around that. And the way we do it is we declare, we use formulas. So Excel knows how to do formulas. You can go to any cell here, and you could say, start with an equal sign, and then put in some formula from Excel, and it might be 3, right? So the choice variable for C is equal to 3, and then use a multiplication sign times the coefficient 1, right? So 3 times 1, and then the second part of that formula we might build could be to add to that 5, or the level of the premium brew, multiplied by, right, so the asterisk is the multiplication, 5 multiplied by 2.5, the profit equation coefficient. Now if you hit enter, you'll see that it calculates to be 15.5. And so we just wrote in this cell over here a calculation or a formula that is the equivalent of writing the equation definition of the profit level. So profit is equal to something. Well, it's equal to an evaluation of its left-hand side of the equation, which we can get from a formula. Okay, and so that's what we have here, and so we should see the same formula here under profit level, and in fact we do, but in some ways we don't. So what I want, the reason I wrote the formula one way here, B2 times B4 plus C2 times C4, so here times here, plus here times here, is I wanted to show you this new way of writing these kind of formulas that's going to help us in these linear programming problems in Excel. And it's a formula that Excel has built in, and it's called the sum product. And it means just what it sounds like. It means take some products, right, multiply two things together, and do that as many times as you want, and then add up all of those products. So sum over the products, multiply coefficients times variables, do it for all the coefficients and all the variables, and then add up all those products, add up all those multiplications, and we'll record that value here. Okay, and so the way Excel does it is this sum product formula is an array formula. So it says, give me the arrays first for the variables, B4 to C4, or sorry, first for the parameters, B4 to C4, then give me the next array and make that one for the variables, B2 to C2. Okay, so it says, highlight this row, B4 times C4, then the second array after the comma here will be B2 to C2 up here, these values. And then what Excel is going to do is say, I'm going to take the first piece of this array, B4, I'm going to multiply it by the first piece from this array, B2, then I'm going to go and do the second multiplication, C4 times C2, and when I finished all those products, all those multiplications, I'll add those together. So in some ways, the sum product is like taking either this version of the formula, multiply something from this row times this row, multiply something from this row times this row, and add them together. Or another way of thinking about it is, if we had some kind of extra row built in right here that said, okay, we need to multiply 3 times this times 1, and I'm going to copy and paste that here. We need to multiply the variable times its profit per unit in there, and then multiply this variable times its profit per unit here. But to get the total profit over here, we would do a summation. We would sum these two cells together, and we would record that value there. And so what Excel is doing is, with this sum product formula, is basically saying, okay, I realize that this is the kind of formula you might have to do a lot, so I'm going to give you a built-in formula so that it lets you specify this row and this row, and what it's going to do is I'm going to cut out this row. I'm not going to make you do this row where you first do the products before you do the summation, right? So you calculate these products here and then sum up all those products, and so this built-in formula keeps us from having to do that. So take some time with it if you need to. Look at the example, look at the help on sum product. That's about all I'm going to say about it, other than it's a huge assistance for these kind of models, because that's the classic form of a linear equation, is to multiply a slope or a coefficient times a variable. And we're going to have very long linear equations that are going to have lots of variables that need to be multiplied by their coefficient, and we're going to have lots of equations. We're going to have lots of constraints in some of these problems. So if we were having to do a partial, either specify each of these equations this way, we would spend a lot of time just writing out the formulas or just inputting the formulas in Excel, or we would have lots of extra rows here where we're just calculating products so that we could later sum them up. Because each of these equations down here, these left-hand side equations or evaluations, are going to be those sum products again. Multiply the variable times the coefficient, add that to this variable times this coefficient, and record that value as the left-hand side. Same thing here. If I double-click, you'll see it's now B8, again referencing back to the variables. Now the other thing that makes this nice is Excel has this feature. If you look here, you'll notice that B4 colon C4, the constraint coefficients, the profit equation coefficients, are just written directly as B4 and C4. But in the variable, array here, B2 to C2, I've put a $sign in front of the B and a $sign in front of the 2, and then the same thing over here, $signs in front of the row and the column indicators. Now what that does is these $signs make what we call hard or fixed, or I think the Excel term is absolute references. And it just says if you want an absolute or a fixed or a hard reference to something, put $signs in front of it. And what that does is when I copy the formula from here, from this, the formula that sits in this cell, and then paste it somewhere, and we get a 0 there. But when you look at the formula, what it does is if I don't have the $signs, it shifts down and says, okay, this new formula is in row 5, so let's shift down and look for coefficients in row 5. But when I go to multiply those by some other array, I'm going all the way back because that reference, that cell reference to the variables is locked in with these $signs. So I'm going to go back up to B2, C2. So let me take that away so you can see the way I've actually built this spreadsheet, these formulas, is I built this equation, or this profit level measure, and then I just cut and pasted the formulas down here, and it says, okay, go find your coefficients, the first piece of this, directly to the left in the row, but when it comes time to find the thing to multiply by, stay locked into the variable row, because everything down here relates to the variables. Okay, and so you'll see that you could do that, and if you want to just test it for yourself, just delete these two formulas, and maybe check, make sure you have the $signs for B2 and C2, and you can just grab this little corner right here and drag those cells down, and then check, and you'll see that the actual cutting and pasting worked just like it was supposed to. Okay. If you need an algebraic representation of what's going on here, then this left-hand side column is an evaluation of everything that's on the left-hand side. So in some ways it's saying I want one cell to hold the value that's like saying if AIJ represents the coefficients over here, any coefficient where J is a row and I is a variable or a column, then AIJ is a coefficient for variable I and constraint J multiplied by variable I, right? And then sum over all the variables. So the summation over the variables of AIJ times XI, and then that must be less than or equal to something called B sub J. Okay, and B sub J are just the limits. Okay, so this entire expression here could be written algebraically like this, but another way to think of it, since we're just kind of implementing a computer model for the first time here, is multiply all the variable choices by the coefficients, add those up, and collect that value here so that Excel has one cell that holds all the left-hand side information, and then it has the fixed value, or our upper limit, that it can compare to on the right-hand side. So it's going to be comparing left-hand side versus right-hand side, left-hand side versus right-hand side. So this is the only way Excel can check this, is if you have all the information on one in this column to be compared to this column. It doesn't know how to deal with inequalities written as equations, but it does know how to compare two cells. It can always say which of these two values is larger, and that's what we'll use when we implement this model. Okay, so we got the coefficients typed in as values here, input as information. The right-hand side of the upper limits for each constraint are entered over here as their own values, right? You'll see that they're just listed as numbers. The prices, or the profit per unit, listed here, and those are the sort of fixed pieces, right? Here, fixed pieces, and here, fixed pieces. What's going to be changing? These are formulas, right, on the left-hand side column, formula for the objective, and then the only thing really that needs to be changing are these, right? So 5 and 5. These variables cells are things that we're allowed to adjust to try to find workable solutions, right? And you can find 10 and 10. Let's put 10 and 10. And we could come down here and evaluate that and say, okay, if I make 10 units of cheap and 10 units of premium, then I will make $35 of profit, except I can't do that because these two constraints, sorry, all three constraints, the left-hand side exceeds the right-hand side, and this condition has to hold. And so this is where I tell you that the representation we have here, Excel doesn't have any way right now of knowing that, of telling you that 10 units of C, 10 units of P is a violation, right? The only thing we have is this column here that I've labeled sign, and it's just notation. It's just a reminder for me. It's a reminder for me that I need to be comparing this side to this side, or this column to this column, and the comparison I have to make is to make sure that this is true. Make sure that this holds as true. Excel's not going to use these values at all. So when we do this, when we set this model up to run in Excel's solution program or solution application, we're not going to use this. This is just for us as sort of a documentation of what we've done. What Excel wants to know is, what are the variables, what are these left-hand sides, right, and what can I compare them to? And I'll tell you, and then Excel will tell you the best choices that you can make, given that this is your objective, and given that these things on the left-hand side have to stay in the boundaries set by the right-hand side. And that's how this is going to work. Okay, so let me jump back to my PowerPoint. Okay, this is again a cutout of the spreadsheet model, variables, column in the columns, constraints and other equations in the rows, and here is just the notes that go with this. I think I've talked through all of these already. So variables and column, equations and rows, where you see the intersection of a column and row, that is a coefficient. So that coefficient converts the variable units to the equation units. So if you want to think about it in that way, cell B4 in your spreadsheet, that coefficient of 1 means every unit of C increases profits by $1. Every unit, in cell C4, the coefficient 2.5, every unit of P increases profits by 2.5, and then you can do the same for cell B7. In the spreadsheet, Excel, how do we deal with equations? Well, that right-hand side versus left-hand side setup. The right-hand side is always going to be that parameter or limit that we've assigned to be an upper, or in some new problems that we get to, lower boundary for the constraint. And then that left-hand side cell, the column of left-hand side, is always going to be that evaluation of the left-hand expression. So whatever is on the left-hand side of our equation, our inequality, we're going to evaluate in one spot, and then let Excel do what it does best, which is compare those two cells. And then another way you might think about that is, let that, that's an error in the you might think of that left-hand side cell, sorry about that, being a dummy variable. So in what you see, that's probably going to say right-hand side in the notes. I don't think I will be able to update those where they're posted for you. But that left-hand side could be like a dummy variable. It just holds whatever the current value for any candidate solution. So you try out solution 10 versus 10 for P and 10 for C, and that left-hand side is always going to hold what that candidate is, or that current value. And so we might call it something like B sub C1. So candidate 1, or constraint 1's candidate B value. And then what Excel actually does is take that candidate value and compares it to the fixed value, the hard limit that's been set by the problem definition. And then, yeah, figure 6 in your handout actually shows you those Excel formulas that go in the left-hand side. So the sum product is what we use, and I've already talked through that. So we got our problem set up. We can go into the spreadsheet, we can play with it, and try to find the solution, right? I mean, that would be something simple to do. I've tried 10 versus 10. We see that that exceeds the profit. I think I did 5 versus 5, and you saw that we weren't using all the resources, so you might want to increase from that. But that would be pretty tedious, and we're already in a computer, so there should be a way for the computer to automatically trial that junk for us and just give us the solution and let us start doing what we do, which is do the economic analysis. So it turns out Excel does have that. It's called the solver package. It's an add-in. So when you install, or whoever installed Microsoft Office on the machine you're using right now did that, there's a fair chance that they did a standard installation. And what happens when Excel installs under the standard application, or the standard sort of setting, and you don't use custom settings, is that it puts in sort of what people use the most, and it doesn't put in the add-ins, but they are sitting there. They have a small install file that is kept there with Excel, so that if you ever change your mind and want them, you can set it up and have Excel add them in. And so it's called an add-in package. So this implementation would let us do that. And so the first thing we're going to have to do is check for it. So look on your Excel, go to this data. I don't know, I call it the data tab, or sometimes, but maybe it's the ribbon, the data version of the ribbon. Whatever it is, go across the top from File, find Data in Excel, and when this changes the things that are shown down here all the way to the right under either something that's called Analyze, or in some versions of Excel it's called Analysis. You should see something that says Solver. If you don't see that, then we're going to have to do the steps to install it, and those steps are here. Go to File, then go to Options. Don't worry, I'm going to show you this. Go to Excel add-ins, go to the Solver add-in, and as an aside, you probably want to see if there's an analysis tool pack there, and grab that as well. And then check for Solver under Data to see that it actually did install. So let me switch over to the spreadsheet, and I'll take us through that. Okay, so you can see I'll go to Data, and I'm sorry, there's no way for me to expand the size of my this visible screen part here. So it's going to be kind of small to see this stuff up in the menus of Excel. But I'm clicked on the Data ribbon or Data tab up here, and all the way to the right you see I have Solver installed. It's part of the analysis block. If you don't see it there, you can go to File, then all the way down, slide down to, on the left here, under File, to Options. And when you click on Options, yeah, I can make that larger, but it won't change the fonts. When you click under Options, you'll see sliding under here, General Formulas Proofing. What we want are the add-ins. Okay, so this is where Excel is storing these things that didn't get installed, but it did keep the installation package with Excel. So if you click on that, you see here the things that have been added in already, and so you can see that I have an Adobe add-in, some kind of tool analysis tool pack, which is what I mentioned to you, and then the Solver add-in. Here's some other ones that I don't have. They're not active, but they could be. So if you're going to do European currency or Euro, you need the Euro symbol. You could add that in. But we're not. So let's go to down here. We have this Manage Excel Add-ins. Just click on Go, and you get this little box. And these are all the ones that are ready to be installed. They just haven't been. And so if you have 10 of hopefully, if you don't have solver, then this is unchecked and you can now check it. And then I'll just make a plug that you could add the analysis toolpack here if you ever want to do regression analysis or some histogram analysis or some other hypothesis testing in Excel. They're all contained in that analysis toolpack, so you could let that install too. But check the box by solver add-in for sure. Click on OK. It won't show it installing for me, but that should it should take almost no time, and Excel should install that for you, and then you go check your data tab, and hopefully it's showing up there. Okay, let me jump back to my PowerPoint real quick. Okay, so let's look at what Solver does. So if you have Solver installed now, then you can open it in that spreadsheet and you'll get something that looks like this. Well, I'll take that back. I think the version I'm giving you of the spreadsheet already has the Solver interface built in. All the information is already added to it. So you'll see it filled in already, but let's look at what the different pieces are. So here I've got a blank Solver parameters input. So the heading, when I open Solver, says Solver parameters. It could say something different if you're in the Apple or Macintosh version of this, or in an older version. But I've just got these numerically identified here, 1 to 6. And so the first thing, this field up here is for the objective cell declaration. So we talked about these declarations of different things that we would have to do in a model setup. Well, the parameters, Solver parameters box here matches up with that quite nicely. So the first one here is where we put the objective cell. So whatever cell of the spreadsheet is holding our profit definition, that's what goes there. The second thing, set the direction of the objective, right? So we're trying to maximize or minimize. You can also hit a target value if you want. We're not going to do that, but there are, I guess, some problems where you might want to try to get to a certain value within a certain tolerance. But we're going to use maximization here. And then the third field is for the variables. Okay, so it calls them changing variable cells. So the cells that Excel, the program that the spreadsheet is allowed to make adjustments to. So you tell it which things it's allowed to move around to try to make large or maximize the objective cell. Okay, so this is where you say what are you allowed to change, and so all of our variables, our choice variables, go here. Then we have this large field for constraints. So this is where we're going to specify all of our constraints, and you'll see out here to the right that it has a whole set of buttons or sort of functions that go with it. Adding a constraint, changing a constraint, removing a constraint, resetting, and then if you have some kind of saved problem with a full set of constraints ready, then you could load it in there. But field 4 is where we define the constraints, and we're not going to be including non-negativity constraints in this space. So non-negativity constraints are so common, and that Excel has a built-in checkbox for them. And so down here in 5, item 5, it says make unconstrained variables non-negative. So basically take everything in 3 and just assign a non-negativity constraint to it, a greater than or equal to 0 equation. And there's some good reasons to use the checkbox version. Now, it's certainly the case that you could leave this unchecked and write in your own equation constraints. But 1, it takes up space, we have to do it, and then 2, Excel's solution reporting and sensitivity reporting that we won't see until later in the course, it sort of expects that you'll use this checkbox, and so if you put the constraints up here, it treats them a little differently than it does this automatic part. And then 6, something new for us. We've never solved one of these before except by graphical means, and so it says I've got some options for you on how do you want to solve this, and that's what you choose in 6. So if you click this drop down, you would see, I think it's called GRG nonlinear, simplex LP, and then the other choice is it's some kind of genetic algorithm. I can't remember, but anyway, there's something else included there. When you go to add constraints, I'll show you. When you click on this button over here that says add, it gives you an input, sort of an input app or an input tool that lets you work directly with the way that we've been set the spreadsheet up. Okay, and so when it wants a constraint, it wants cell references, and what it does is it wants to compare a left-hand side cell reference to a right-hand side of a constraint. So tell it the fixed value over here for the constraint, give it the cell reference where you've added up, done that sum product for the left-hand side here, and then you'll see there's a little selector arrow here that says click on this and you can choose between less than or equal to, greater than or equal to, maybe some others, but that's where we'll set up all of our constraints. So put the left-hand side value, the sign, right? But you'll have to select it here. You can't use the one you can't use a cell reference for the sign, and then put the right-hand side in. If you have more constraints to do, you just keep clicking add until you get to the last one. When you put the last one in, you click OK, and it fills in. And this is what it would look like when it's filled in. So here, I actually put them in as a bundle, so you can highlight the entire bundle from E7 to E9, as long as they have the same thing in between, the left-hand side and the right-hand side. You get less than or equal to, and what it does is it just matches up E7 to G7, E8 to G8, and E9 to G9. Says each one of those by themselves have to be less than or equal to, and that's what the constraint field looks like. And then we would click solve, and so let's switch out and go to our spreadsheet and take a look at this. Okay, I've cleared out my solver so that you can watch me put in each of the pieces. Here, I'm going to go ahead and actually reset the variables to 0 before I do that. Yeah, so I'm going to click on solver, and you see here that I have this empty set of fields that I need to fill in. Okay, so the first thing says set the objective, and so I can right click. You could either type in the cell reference, or since my cursor's there, I could just click there. But probably the easiest way, or the most deliberate way, is to click this little red arrow, and it may be a different colored arrow depending on what version of Excel you have. But if you click this little thing over here, the switcher on the right, it gives you the field that looks like this. And now I just highlight my profit cell, that's my objective, and you click this again and it switches you back to the parameters, the solver parameters box. So I've got the objective set. Now I need the direction, maximize, right? You could switch to minimize. That won't work here, but we'll click on the max. And now I'm going to do the same thing I did before. When down here for the variables, you could put the cursor there and select the variables, but I'm going to click this switcher over here. I don't know what these are called, but I call it the switcher. So it switches to something that looks like this, and then I just highlight both variable cells. So B2 and C2. Click the red little switcher thing again, and now my variable cells are included. And so what's left is I need to get my constraints. Sorry, I hate sliding that around. Left-hand side comparisons to right-hand side in. So in the picture, in the slides, I had all of these collected together and said compare them one by one against their counterparts in the right-hand side. But let's put them in the version you open. Hopefully it'll look this way. I'm going to put them in one by one just so we get used to seeing how this works. So it wants a cell reference for the left-hand side. This is going to be the formula for the left-hand side. And here I'm not going to click the red thing. I'm just going to highlight it. So you get E7. And then I told you there were different options you could put in between the left-hand side and right-hand side. So we have less than or equal to, equal, greater than or equal to. And then we have some other ones, integer, binary, and I don't even know what that one is. Might be, to check, see if they're different, I guess, but I'm not sure. Less than or equal to is the sign I want for not just this first constraint, but all my constraints. And then I can put the cursor over here and then click on the right hand side constraint value. When I get the first one put in, I'll click on add, and it clears these fields and says go ahead and put your second constraint in. So that means I'm going to select the out of the 8th row now. So I've got E8 needs to be less than or equal to, move the cursor, this right hand side value of 40. Click add one more time, clears out the fields, so the cell reference here needs to be out of row 9. It needs to be less than or equal to the right hand side value in G9. I get to the last constraint, I click on OK, and we check my solver inputs here. E7 versus G7, they're all less than or equal to, and so you can kind of see that you if you keep this solver parameters open, and you can just check, and as long as you put these signs in correctly to sort of document your setup for yourself, then you can check quickly here to make sure you put them all in correctly. And that gets us to the end, right? So I've got the checkbox for make unconstrained variables non-negative. Those are my non-negativity constraints. And I've got the simplex LP chosen. I told you there's some different options here. So the first was GRG nonlinear. Simplex LP is the one we'll be using. It's the second one. And then the third one is how I said genetic. It's evolutionary. It's like a genetic algorithm, though. It's a complex solver. We need a simple solver. We need simplex LP for this linear problem. And we click on solve, right? So that's all there is left to do. Click on it. And I have two screens open, so you're going to see me sliding something over here. And you get the I completed my work report from Excel. So let's see what it says. Up here it says solver found a solution, all constraints and optimality conditions satisfied. It says the same thing down here. And then it gives us some options. It says keep the solver solution. You can see up here that it changed the value for the variable level of C. It changed the variable level for P, which gives a new profit level, right? It updates the profit level, and then it changes these left-hand side evaluations, right? So everything here is responding. You can check your constraints. This is less than this. This is less than or equal to this. This is less than or equal to this. So everything holds. This is the profit level, and Excel's telling us it's the best. So that seems pretty good. So that seems like we would keep that solver solution. As an alternative, we could restore the original values. Typically, that's something you might do if you get an error. So if we solve this and it said solver encountered an error of some kind, we might restore the original values. This would let us, if we click this, then clicked OK, it would take us back into our problem setup in the solver parameters box and let us make some changes. Over here, if we think we have a good solution and we want to be sure that we can pull it back up sometime, because we're going to try some different things, right, by returning to the solver parameters dialog, it has a scenario save option, so we could save that. No point in doing that here. And then finally it has some reports we could look at. It has an answer report, a sensitivity report, and a limits report. If you wanted to view those, you just highlight them, right? So just by putting your mouse on there and clicking, it'll make them blue, and then when you hit OK, it'll use new Excel sheets to print those reports out for you. I'm going to leave those unclicked because I don't want to get to the reports yet from solver. So I'm just going to click OK. The only thing that's going to happen is going to keep the solver solution for me. And then I could start doing some of my work here, some of my analysis, some of those things I started doing right at the beginning, where I said, if we look at these and we see that they cost the two variables, the cheap brew versus the premium brew, they have sort of the same usage rate here, but the savings right? The thing that makes the cheap brew is, one, we can't charge as much for it, but one of the things, the thing we have to consider is we're not charging as much for it, but it's not using up our firm resources as quickly. Here it's half as fast, and here it's 1/3 as fast, right? So we're using bottling time up less quickly with the cheap brew, and quality control time less cheaply with the cheap brew. And if we look at this information, you can see that these two things being relatively cheap or relatively cheap brew using bottling and quality control less than the premium brew is important in this problem, because these are binding constraints. These are the actual things that are limiting this problem. Okay, so when we talk about why are profit levels at 22.5 and why is this the best combination, well, the third piece of that story, where you say here's our predicted profit level, here's our best plan, well, the third piece of that solution story is to come down here and say, what are the limiting factors that cause this to be the best plan? What are the limiting factors that cause profits to top out at 22.5? And it turns out it's these binding constraints, the constraints where the left-hand side is equal to the right-hand side. And why is that the case? Well, they use the factor, both choices use this factor at the same rate, but it's not that important of a factor in this problem the way we've set it up, because we didn't even use all that we had available. So it doesn't really matter if you're cheap or expensive in terms of using pre-fermentation time, because we have more than we need. It's not a very limiting resource for the firm under the conditions we've set up. Okay, so it's not a binding constraint. We actually have excess time available there in the pre-fermentation part of the factory, and so it's not going to be an important issue when we start thinking about comparing the rate of return. Right, so the profit equation compares cheap versus premium, or C versus P, in terms of the rate of return, and then all of these compare cheap versus premium in sort of the cost of production, right? Not in the physical or money cost, but in the resource cost of production. Well, once we solve the problem, we see that this one is not really an important piece of the cost of production story, because we don't use all the resources, but these resources show up as limiting, and so here the cost terms are important. And so one of the things that we're sort of prepared to do now is say, okay, I know that cheap brew brings us less return per unit than premium brew, but if its cost is relatively small compared to premium brew, we might produce some of it. And if its cost is relatively small by a large ratio, we might produce quite a bit of it or more of it. And that, in fact, is our solution here. We have doubled the amount of cheap compared to premium brew, and that's being driven by these constraints. It's being driven by the fact that, yes, we are earning less on cheap brew, but it's using up our resources at a slower rate, which means that we can get more volume out. So producing more volume of the less expensive brew may be a reasonable solution, and this mix is the solution. Okay, so let me get back to our PowerPoint for a little bit of wrap up. Oh, sorry. Okay, so that is all the wrap up I have. So I guess we're not going to look at this. I will just say that this lab, even though I've talked about a lot of things, was designed to get our first solution together. I think you can now, with this lab walkthrough, you can solve this problem. You could consider some changes to the problem. One of the things I always encourage people to do when they first learn Solver is, let me open my spreadsheet back up, sorry, is to make some changes. What does it mean, right? So if we have this solution and we're willing to produce 10 units of cheap, 5 units of premium, 10 units of cheap, 5 units of premium, because even though the returns are less, the costs are less. Well, what does it mean if this got lower? What happens if this becomes 0.5 or 0. Let's go with 7.5? Well, you plug that in, and here's the danger. Here's the problem with Excel. It's going to update all these values for you. You say, well, okay, if we update this to 0.75, the profit level falls to 20, but does it? Well, no, it doesn't, right? Because what we haven't done yet is reconsider what's the best solution when the profit per unit for cheap falls from 1 to 0.75. And so in fact, what you would need to do is to rerun solver and see if it tells you to change the solution. And in fact, it does. It says if this price for 1 falls down by 25 cents, 25% reduction, then you are going to make a switch in the production plan from producing a mix of cheap and premium all the way down to producing only premium. And so this is one of those situations where I'm not going to keep the solver solution. I'm going to restore the original values. So back to the solution we had, and then I want to remember to change that profit equation value back to 1, and that's the solution level we have. Okay, I think that's probably enough for us to get through. I will encourage you to read the Notes 1.2 handout that goes with this. You'll see some other things discussed in that handout that use this graphical working space and the actual feasible space graph that's plotted here, as well as some of the corner point calculations and so forth. But I will be talking about some of that other stuff, the graphical solution and the corner point theorem kind of calculations in our next lecture. But for now, our key focus is being sure that we get through solver and learn the implementation steps. With that, I'll sign off here and start processing this video.